Welcome back. Today I would like to talk to you about double integrals over rectangles. And I've started by drawing this little picture for us so that we can kind of get a feel for what's going on here. So I've drawn in the three axes. I've got my x-axis here, got my y-axis here, my z-axis up here. And then what I've done is I said, okay, I've got a rectangle over which there is a surface. So I've got, on the x-axis, we're looking at a point A to point B, and on the y-axis, from point C to point D. So if I look at the rectangle formed by those two intervals, you can see the rectangle down in the xy plane. This dotted line here, over here, down here, and over here. Okay, and then you kind of see this surface that's sitting up above that rectangle. Okay, so someone might ask the question, okay, so what's the volume that's underneath the surface? So if you look at this whole, if this is kind of the base of your surface down here, and this is the top of your surface up here, then what is the volume of that shape that's drawn right there? Okay, ultimately, this is the same as kind of taking an area in 2 dimensions, and we just integrate. Okay, so that shouldn't be a surprise. But how do we actually set up an integral for such a thing? Well, we do it very similar to what we would do in 2 dimensions. In 2 dimensions, we'd break the interval up into a lot of little pieces and then start forming rectangles. But in this case, we do something a little bit different, and that is that we break this rectangle at the bottom up into little rectangles. But let me show you what I mean. So I'm drawing in these little rectangles, and then we go the other way as well. And you can see I'm breaking up my rectangular region into a bunch of little rectangles. Then what I do is I do the same thing that I would do in 2 dimensions. Maybe I'll draw something down here in 2 dimensions as well. So let's just say I had a function down here. This is f of x, and I was integrating it from a to b, and I wanted to know what's the area under the function between a and b. The first thing I'd do is I'd break it up into pieces, and then what I do is inside of each pieces I choose a representative point to be where I measure the functional value, and then I draw in a rectangle, and I find the area of that rectangle. Then I find a special point in the second, use that as the functional value, and then I calculate the area of the second rectangle. So I'm going to do a very similar thing here, in that in each of these little rectangles I need to choose a point to be the representative point in each of those little rectangles. And then for each of those points I go up to the surface to see how high the box should be. So here we get a box, and I will take the volume of that box to represent that little rectangle at the bottom. So I'll add the volume of that one box, and then I'll continue to do that for every point in each of my rectangles and add all of those volumes. Now, at the top here, this is flat on top. It's not curved like the curve, but that's okay because remember over here, these are flat on top. They're not curved either. But as I break this rectangle into smaller and smaller little pieces, the air is going to get smaller and smaller just like it did in 2 dimensions. So really it's very, very similar. So let me write something down here. really what I'm looking to do is the volume is going to be equal to the limit as the maximum of delta x sub I times delta y sub I goes to 0 of the sum. I'm sorry, I put in something that is not so good. This should be a j. Delta y sub j. So it's the limit max delta x sub I delta y sub j goes to 0 of the sum I going from 1 to n let's make that an m of the sum j going from 1 to n, so that m and n can be different, of f of x sub I star okay, I'm going to call this x sub I j star y sub I j star times delta of a sub ij. Now, what am I talking about here? So we had that region down in the bottom, the rectangle that I was working over. Let me draw it again. So here's my A and my B. Here's my C and my D. And so I get this rectangle in the XY plane, right? And then what I do is I'm going to cut this up into pieces. And so then what I'm going to do is I'm going to say, okay, really what this is it's a box. And how do I calculate the volume of a box? I take the area of one of the pieces of the box, and then I multiply that by the height of the box. And I get right there. And then I take the area of the base of the next box and I multiply it by the height of that box. And you get the idea. So we start adding up all these boxes. So this is the area of the base of the box. This is the height of the box. So what we're doing is over the x direction and over the y direction, we're adding up a height times a base area to get a volume. And then we're doing that, we're taking the limit as the size of those boxes, or the area of those boxes, goes to 0. Okay, so given that, we can say the following. So, the double integral of f over the rectangle capital R is the double integral, and we write a little r at the bottom for over the rectangle R, of f of xy dx dA, and what I mean by dA is given a change in the area of those little rectangles, so given a small change in area, is equal to the limit, and this is exactly what we wrote before, of the max over delta x sub I delta y sub j goes to 0 of sum I going from 1 to m, sum j going from 1 to n, of f of x sub ij, y sub ij, both stars, times delta a sub ij. So this is just a big Riemann sum, and we can simplify it down to a double integral. Okay, if this limit, this big limit right here, if that exists, then we call this function integrable. So if the double integral exists, we call f of xy integrable. Okay, so now we need to talk about what are called iterated integrals. So let me write down an iterated integral. We could have something like the integral from a to b, integral from c to d of f of xy dy dx is called an iterated integral. Okay, so one thing I want to say right now about these iterated integrals is suddenly this dy and this dx back here, they're very, very important to us. And the order in which they're written in is very, very important to us. Because what's really happening here is we kind of have an integral inside of another integral. So this is an integral. You can kind of think of there being a parenthesis right here. There's an integral with respect to the variable y. And then when I'm done taking that integral that's on the inside, I take the integral that's on the outside, that's an integral with respect to the variable x. And if you mix up the dy and the dx and you write these in the wrong spots, it's completely nonsense. So you have to be very careful that you know what you're talking about, and you're saying that, okay, c to d, that's in the y direction. A to b, that's in the x direction, just like it was on our picture. Okay, so let's do an example of one of these so you can kind of see how it works. So let me erase real quick, and I'll do an example. So let's evaluate the iterated integral from 0 to 3, and then from 1 to 2 of x squared y dy dx. All right. So remember, I can think of this as just there's an inner integral that I have to compute, and then there's an outer integral that I have to compute. But I don't need to really worry about that outer stuff like the 0 to 3 and the dx. I do nothing with that at the beginning. I just compute this inner integral that I'm going to circle right here. That's all I need to worry about to begin with, is that inner integral. So let's do it. And so I want to take the antiderivative of x squared y with respect to the variable x. And just like when we did partial derivatives, I can just treat the x stuff as if it's constant for right now and just take an antiderivative with respect to y. So I've got a constant times y. So what's the antiderivative of a constant times y? Well, first of all, I'm going to write integral from 0 to 3. And then if you'd like, let's write in a bracket just to kind of keep track of what's going on inside. I take the antiderivative with respect to y, and I get x squared. And then the antiderivative of y is 1/2 y squared. So I'll just put in the 1/2 y squared, and that's evaluated from 1 to 2, and then all of that dx. Okay, so now what's being evaluated from 1 to 2? Y, not x, because I'm taking the derivative right now with respect to y. So the 1 and the 2 are being plugged in for y. So if I do that, I still have an integral from 0 to 3 of, if I plug in the 2 for y, I get 4 over 2 times x squared, minus I plug in the 1 and I get x squared over 2 dx. Okay, so if I subtract that, I just get the following. I get integral from 0 to 3, and then I've got 4/2 x squared minus 1/2 x squared. That's 3/2 x squared dx. Okay, but now this is just a nice integral that I'm used to. It's an integral in x, and I know how to do this, so let's just take the antiderivative of 3/2 x squared, and I get that that would be, the x squared would go up to an x cubed, and I'd divide by 3, so I'd get 1/2 x cubed evaluated from 0 to 3. If I plug in 3 cubed is 27, so I get 27/2, and if I plug in 0, I get 0. So the answer here should be 27/2. Now, an interesting question is, what did I just do here? Well, I just computed an iterated integral, and can I necessarily say that that thing is a volume? Well, to say that that's a volume, it actually is, but the only reason it is because x squared times y is always positive in the rectangle over which I am integrating. So this actually is some volume in units cubed. So that is a volume. But it could be that this thing dips down below the z equals 0 plane, and in that case you have to be a little bit more careful, just like we did in 2 dimensions. Okay, so now I need to write down something that we call Fubini's theorem. So Fubini's theorem. And Fubini's theorem says the following. If f is continuous, on the rectangle, capital R is equal to all the points xy such that A is less than or equal to x is less than or equal to b, and c is less than or equal to y is less than or equal to d, then we have the following: that the integral, iterated double integral over a rectangle R of f of xy dA, which is our nice double integral over a rectangle, is equal to the integral from a to b, integral from c to d of f of xy dy dx. But that's also equal to the integral from c to d, integral from a to b of f of xy dx dy. So it doesn't matter what order that I do the integral in if I take the antiderivative with respect to y first here, or if I take the antiderivative with respect to x first here. You can do it either way, but it does matter that you match up the intervals. So in other words, c to d happens in the y direction. Here, c to d happens in the y direction. If you mix that up and you accidentally, if you just switch these two without switching these, then it's just wrong. Okay, so you got to make sure that if you're integrating in the y direction from c to d, that matches up with the dy. So if you're integrating in the y direction with c to d, that matches up with the dy. That's important. So that's the one place where you can really kind of mess it up, is you write in the dy dx in the wrong order, and then it just is kind of nonsense. Okay, so as long as you're being careful about that, everything's fine. Okay, let's do another example so you can. So, an example. Let's evaluate. The double integral over r of x y squared divided by x squared plus 1 dA, where the rectangle R is equal to the set of all points x, y, such that 0 is less than or equal to x is less than or equal to 1, and -3 is less than or equal to y is less than or equal to 3. Okay, so we need to set this up, and it doesn't matter which way we do it, if we set up where we're integrating the x first or in terms of y first. But when I look at this thing, it just seems to me like I'd rather start by integrating in terms of y, because it's easier. So I'm going to set this up where I'm going to put in the xy squared divided by x squared plus 1. And I said the thing I want to integrate with respect to first is the y and then the x. So the inner integral gets the y bounds, and the y bounds are from -3 to 3. And the outer integral gets the x bounds, and that's from 0 to 1. So now this thing is all set up, and we can go ahead and take the integral. So the first thing we're going to do, think about this as a big parentheses right here, is I'm just going to look at that inner integral. So I'm integrating with respect to y, so the antiderivative of y squared is just 1/3 y cubed. So the 1/3, if I wanted to, I could just write the 1/3 outside the integral, and 1/3 is a constant. It passes through any of the integrals, so I'm just going to write the 1/3 all the way outside. So it's 1/3, 0 to 1, so now I'm taking the antiderivative, so I get x over x squared plus 1 times y cubed. Remember, it's 1/3 y cubed, but I wrote the 1/3 out here. Evaluated from -3 to 3 dx. Now I can plug in my 3 and my -3, and I get 1/3 integral from 0 to 1 of, if I plug in 3 for y, I get 27 times x over x squared plus 1 minus, now I plug in minus 3, and I get minus 27 x over x squared plus 1. All of this dx. So I can rewrite this again. Let's say that this is 1/3 integral from 0 to 1 of 27 minus minus 27 is 54. Now if I wanted to, I could go ahead and write that 54 outside the integral, and I think I would like to do that. So I'll just put it in right here. This is a 54. And then inside I'm just left with x over x squared plus 1 dx. Okay, so I have 54 thirds. By the way, is that 54, is that divisible by 3? Yes, it is. That's 18. So I'll change that in the next step. And now I need to take an antiderivative of x over x cubed plus 1. What is the derivative of x squared plus 1? Well, the derivative of x squared plus 1 is 2x. But 2x is almost setting on top there. So if I were to bring in a 2, this is just a natural log. So let's bring in 2 from that 54 thirds. 54 thirds is also known as 18. So let me write it this way. So 18 is 9 integral from 0 to 1 times 2. So 9 times 2 is 18, but I'm going to put the 2 up with the x over x squared plus 1 dx. But now the derivative of the bottom is the top, and that's exactly the form of a natural log. So now I could write this as, this is 9 times natural log of absolute value of x squared plus 1 evaluated from 0 to 1. Okay, let's plug in the 1. If I plug in 1, I get 2 on the inside, so I get 9 ln of absolute value of 2 minus 9 times ln absolute value of 1. But ln of 1 is 0, so this term's just gone, and I'm left with 9 ln, I guess absolute value of 2, but the absolute value of 2 is 2. And we get our answer. Okay, so these really aren't that bad. We do have to remember how to take an antiderivative, and we have to make sure we remember which variable am I taking the antiderivative with respect to right now. But other than that, it's not too bad. Okay, let's try another one. So, an example. Let's find the volume. Of the solid in the first octant bounded by the cylinder z is equal to 9 minus y squared, and the plane x is equal to 2. Okay, so when you come up with a problem like this, it's very nice to be able to get a feel for what does this actually look like. So I'm going to do my best here to draw this for you. So first of all, let's just draw our axes. Here's my z-axis, my x-axis, and my y-axis. Here's x, y, and z. And then we have this function, z equals 9 minus y squared. And they say it's a cylinder, but it's not the type of cylinder that's just this, like a can of Coke type cylinder. This is a cylinder where in two directions this is a function, but the third direction there's no x in there, so it can do anything in the x direction. So what does z equals 9 minus y squared look like? That's a parabola that starts up at 9. So up here is 9, let's say, and it opens down in the y direction. So going this way, we kind of go this way and this way in the y direction. So here's the negative y-axis. Okay, and I could draw the negative x-axis back if I wanted to. Okay, so that's how this goes, and it keeps going, of course. But I'm just concerned with the first octant. Well, what am I talking about, the first octant? We know about quadrants in 2 dimensions, but how many, so to speak, they're not quadrants in 3 dimensions, but how many of those types of things do I have in 3 dimensions? Well, there's, on top, you see 1, 2, 3, 4, and then on bottom we have another 1, 2, 3, 4. And so there are 8 what we would call octants. And the first octant is where all of the x, y, and z, where all of those guys are positive. So we're talking about the octant that we're kind of looking at right in front of us right now. Okay, where x's and the y's and the z's are all positive. Okay, so I'm not as concerned with this piece back here, because this piece is not in the first octant. But now we know that the x value can be anything. So in this direction, we just have a bunch of parabolas. You see what I mean? And back here, we have more parabolas. So you get the that's what this thing looks like. It's just kind of this hill that stretches infinitely far in both directions. All right. Now, what this says it's also bounded by is the plane x is equal to 2. Well, what does that look like? Well, now let's back up a little bit since we know what this, and I'm going to erase a little bit of what I've drawn because we know what it looks like. Okay, so the plane x equals 2, if I come out here 2 units, is just the plane that goes straight up and down through that point. Goes through this point 2. And so now if I stretch this guy back and it's cut by this plane, and I know I'm in the first octant, then I start seeing the shape that I'm interested in. And so here's my shape. And you can see it's kind of this little like curved wedge shape. That's the solid that I'm trying to find the volume of. Now, this is not easy when you have not done it before to draw these shapes. And I would really, really encourage you, draw the shape. Draw it. Take the time. It's not one of these things that you're going to do it in 5 seconds. It might take you 10 minutes to really feel good about that I've drawn this shape the right way. But it's super important that you do it and that you kind of understand what this shape looks like. Because if you can't see the shape, then you really are at a disadvantage later when we're doing more complicated double and triple integrals. So you really need to have a feel for this shape. But you can see now that really this is a rectangle on the bottom in the xy plane. And over that rectangle, I have some function. And the function that's over the top is this z equals 9 minus y squared. So how am I going to set this up? So the volume that I want here, v, is a double integral. And it goes from something to something in one direction and something to something in the other direction. Well, in the x direction, this is pretty clear. This is from 0 to 2. So I need to decide what I want to integrate with respect to first and what I want to integrate with respect to second. It doesn't really matter so much. So let's decide we're going to integrate with respect to y first and then with respect to x. And the function that is on top up here, this is 9 minus y squared. So if the x's range from 0 to 2, well, what do the y's range from? Well, from 0 to something out here. What is that point? Well, it's where the function, if I plugged in that that z is 0, what would I get? Well, I'd get that y squared equals 9, or this is equal to 3. Okay? So remember, if z is 0, right, at this point, then what would be y? So just plug in 0 for z, solve for y. I get that I would have a 3. Okay, so now we're ready to go. So let's do the work here. So let me just rewrite this on a different page now that we have our integral, and I'll solve it on a new page. So I've got that my volume that I'm looking for is the integral from 0 to 2, integral 0 to 3 of 9 minus y squared, squared, dy dx. Okay, so first we want to take the antiderivative of this thing with respect to y. So I get 0 to 2. That just stays for right now. Now I take the antiderivative of 9 minus y squared with respect to y. So that would be 9y minus 1/3 y cubed. All of that evaluated from 0 to 3. And then I still have a dx out here. So now let's evaluate that from 0 to 3. And I get integral from 0 to 2. Plug in the 3. I get 27 minus 1/3 of 3 cubed is 27 dx. Let's simplify. That's integral from 0 to 2 of 27 minus 1/3 of 27. 1/3 of 27 is 9. So that's just 18 dx. I suppose if you wanted to, you could just pull that 18 out of the integral completely and just go integral 0 to 2 dx. Remember that there's a 1 in here, if you like. So the antiderivative of 1 is x. So I get 18 x evaluated from 0 to 2. So I get 18 times. If I plug in the 2, I get 2. If I plug in the 0, I get 0. And 18 times 2 is otherwise known as 36. So this is 36 units cubed of volume. Sound good? Time for some homework.